Hi boys and girls, this is lecture 1.8 in Unit 1, the topic Exponentials and Logarithms. We're going to start with a discussion of exponential functions. An exponential function has the form y equals ab to the x. A is a coefficient, b is the base of the exponential expression, and the exponent is the variable x. We've had positive numbers, negative numbers, integers, fractions as exponents, but we've never had the variable there. Moving the variable into the exponent position is what makes this an exponential function. There are exponential growth functions and exponential decay functions. The difference between these two is determined by what b is. If b is greater than 1, then the function y equals ab to the x is an exponential growth function, and in this case b is called the growth factor. When b is between 0 and 1, then the function y equals ab to the x is an exponential decay function, and in this case b is called the decay factor. Now let's graph a couple of these functions. After all, a lesson without graphing is like a day without sunshine, and we certainly can't have that, boys and girls. So notice in this first example that b is 2, which is greater than 1, which means this is going to be a growth function. Let's use these x values, -2, -1, 0, 1, and 2. Now 2 to the -2, let's take a moment to realize that this is really 1 over 2 squared, which is 1/4. 2 to the -1, again, is really 1 over 2 to the 1, which is 1/2. 2 to the 0, of course, is 1, 2 to the 1 is 2, and 2 to the second power is 4. Let's plot these points. -2, 1/4. -1, 1/2, 0, 1, 1, 2, and 2, 4. And here is an exponential growth function. Notice the domain is all real numbers, but the range is y greater than 0. If you think about it, there's nothing you can put in for x that would make this entire expression equal 0. So y equals 0 functions as an asymptote here. Now let's move to the second example. Notice here that b is between 1 and 0, so we're going to have a decay function. Let's use the same x values and plot some points. This is going to be 1/2 to the -2, and we need to remember that the negative flips the fraction, so this really becomes 2 over 1 squared. 2 squared, of course, is 4. 1/2 to the -1, again the -1 flips the fraction, this becomes 2 over 1 to the 1 power, which of course is 2. 1/2 to the 0 is 1, 1/2 to the 1 is 1/2, and 1/2 quantity squared, of course, is 1/4. -2, 4, -1, 2, 0, 1, 1, 1/2, and 2, 1/4. And this is an exponential decay curve. Again, the domain is still all real numbers, the range y greater than 0. That would change, of course, if you had a vertical shift, which brings up our next slide. Let's do some more graphs with transformations. Notice here in this first growth function, since this is a 5, we would have a horizontal shift, a vertical shift, a reflection, and a dilation. In this decay function, since our b here is 1/2, we have a horizontal shift, a vertical shift, and a dilation. I think I'm going to bring up my old friend TI-84 to help us with this graph. Now when we go to the y equals menu, let's be careful when we enter this function to make sure that we do not make a syntax error. This is -2 times our base is 5. And we're raising it to an expression x minus 1, so make sure you put that in parentheses. Then plus 1, which of course is our vertical shift, and this is our graph. -2 times 5 to the x minus 1 plus 1. It looks like most of the action is taking place, let's say perhaps from, oh, I should have pushed the graph button. Let's say from about Oh, it changes the y values. -2 to say +2. Not a lot going on here that we're going to be able to capture in this little frame, but let's plot those points. We would never graph without plotting some points. We would never try to freehand this. It's not going to be as accurate as if we actually plot some points and connect the dots. Remember, those ordered pairs could come from your calculator, but you should take the time to list them and plot them. This is -2.984. Then we have -1.92. 0 is 0.6. 1 is -1. And 2 is -9. So -2.984, really close to this. -1, not a whole lot of difference. Then we have 0.6 around here. Then 1 is -1, and of course 2 drops off to -9. Not a whole lot to work with, but we do get the shape of the graph here. And let's see, there we go. Of course, we would want to check with the actual graph to make sure that we've done things correctly. Notice our domain is all real numbers and the range y values less than 1 because of this vertical shift. Now let's move to this other graph. We have, in this case, it's going to be a decay function. Again, be careful when you're entering this into your calculator. We're going to have 2 times, I'm going to put the fraction 1/2 in parentheses, and of course once again raise it to the power x plus 1, which should also be contained in parentheses, and then our vertical shift here -2. And then this becomes our graph. Notice the action of the graph, I would say, is happening maybe from -3 to say +2. So those are the points I'm going to plot in my table. -3 is a 6, -2 is a 2, -1, 0. It's kind of nice to be able to read them right off the table from our graphing calculator though. And then we have 1, -1.5, 2, -1.75. Of course, now approaching the asymptote -2. Let's plot these points. -3, 6, which is up here, -2, 2, 0, -1, 0, 0, -1, 1, -1.5, 2, -1.75, and here's our exponential function. Again, the domain is all real numbers. The range in this case, y greater than -2. We shift from graphing exponential growth and decay functions to using exponential growth and decay models. When a real-life quantity increases or decreases by a fixed percent per time period, a fixed percent, that's key, the amount of the quantity after a certain period of time can be modeled by this equation. Y equals A times the quantity 1 plus R or 1 minus R to the t power, where A is the initial amount and R is the percent increase or decrease expressed as a decimal. In a growth model, it's going to be y equals A times 1 plus R to the t, and 1 plus R would be the growth factor. In a decay model, the equation would be y equals A times the quantity 1 minus R to the t, and the quantity 1 minus R is the decay factor. Imagine you have an initial population of, say, 4,000. If it's increasing by, say, 5% a year, you would have y equals 4,000, 1 plus 0.05 to the t power. Or if it was decreasing by 5% per year, it would be y equals 4,000 times the quantity 1 minus 0.05 to the t power. Let's look at this with an example. Medicine in the bloodstream. When a person takes a dosage of I milligrams of ibuprofen, the amount A in milligrams of medicine remaining in the person's bloodstream after T hours can be modeled by this equation. A equals I times 0.71 to the T power. Now I'm going to ask you a question, and even though I may not be able to hear your answer, I'm going to try to intuit what your answer is. Is this a growth or decay model? And how would you be able to know? I believe I hear you, and you're absolutely correct. It is a decay model, and the way that you can tell is inside here where the decay factor is. Remember, this was 1 plus something or 1 minus something. The fact that it's less than 1 means we subtracted something. Well then, what is the percentage increase or decrease per hour? Since we subtracted from 1 to get 0.71, 1 minus 0.71 tells you what the percentage decrease was. 0.29, which is 29% decrease. Good job, boys and girls. Now that you've answered that question correctly, I will show you the graph of this function. You can see that after 1 hour, the amount left in the bloodstream is 0.71 times the initial amount. After 2 hours, it's 0.5 times the initial amount. And after 3 hours, it's 0.36 times the initial amount. It wouldn't make sense for this to be a growth function. After all, after taking ibuprofen, you're not going to find after a certain period of time that you have more milligrams of ibuprofen in your bloodstream. Obviously, it's going to lessen as your body flushes out the medicine. Now, let's look at a specific example with a specific dosage. With an initial dose of 200 milligrams, how much ibuprofen is remaining in a person's bloodstream after 1.5 hours? Well, let's see. We have A is equal to our initial amount, 200, and then of course 0.71 to the 1.5 power. Let's plug that in and see if we can get an answer. We're going to say 200 times 0.71 to the 1.5 power. And we find out that there are about 119, say 120 milligrams left after 1.5 hours. And that's how you use an exponential decay model. And of course, it's similar for an exponential growth model. Functions involving e. E, the number, not the letter. The history of mathematics is marked by the discovery of special numbers such as pi and I. Another special number is denoted by the letter E. This number is called the natural base E, or the Euler number, after its discoverer, Leonhard Euler. It's approximately equal to 2.718281828, and it continues on forever without stopping, with no pattern. It's irrational, just like pi is. It's a fun little number. Let's see what we can do with it. Graphs of natural base functions. A function of the form y equals ae to the rx is called a natural base exponential function. Rather than a base like 2 or 1/2, you can have e as a base to your function. The function is a growth function when r is greater than 0, and a decay function when r is less than 0. So notice that you have a coefficient of the variable now in the exponential position. If that number is positive, as it is in this case, a growth function. If it's negative, as it is in this case, it's going to be a decay function. Now, since e is this decimal, most of the time when you're graphing these, maybe all of the time when you're graphing these, you would want to use a graphing calculator just to graph the decimals that are going to occur in these functions. We're going to switch gears now and talk about logarithms, which are the inverse operations of exponentials. What is a logarithm? Well, we know that 2 squared is 4. 2 cubed is 8. However, for what value of x does 2 to the x equal 6? Now, since we know that 2 squared is 4 and 2 cubed is 8, 6 is between 4 and 8, so we might deduce that this exponent has to be between 2 and 3. And of course it is, but what is it exactly? There's nothing we could do numerically to figure this out. Is it 2.4, 2.5? How accurate do we need it to be? Therefore, mathematicians define this x value using a logarithm and write x, the exponent that we're looking for here, is a logarithm base 2 of 6. And so these tables of logarithms were created to deal with the exponents that are not common ones like 2 squared or 2 cubed, but 2 to the what power equals 6 or 2 to the what power equals 5. This is where we come up with a logarithm. Now look at this relationship. Log base b of y equals x if and only if b to the x equals y. The base of the exponential expression is the base of the logarithm. The exponent of the exponential expression is the answer. It's on the other side of the equal sign of the logarithmic expression. And y, the answer b to the x equals y, is the argument of the logarithmic expression. So we need to be familiar with both forms of this relationship. This definition tells us that the equation log base b of y equals x and b to the x equals y are equivalent. The first is in logarithmic form and the second is in exponential form. So let's evaluate a few logarithms. Log base 4 of 64 is what? Is what exponent? Because it's asking us 4 to the what power is equal to 64. Hopefully you're aware that that's a 3. Here we have log base 1/5 of 125 is what? So we write this as 1/5 to the x power equals 125. Well, maybe we don't know this one quite as easily as we knew the previous one, so what we're going to do is rewrite both sides of the equation so that they have the same base. I can rewrite 1/5 and 125 so they both have a base of 5. This can be 5 to the negative 1 to the x power, and this of course is 5 cubed. Now since this is a power to a power, this is 5 to the negative x, negative 1 times x, equals 5 cubed. Now that the bases are the same, I can drop the bases and just make a little mini equation with the exponents. Negative x equals 3, therefore x equals negative 3. Let's do this again for our last example. Log base 36 of 6 is what? It's asking us what exponent of 36 is equal to 6. Again, let's rewrite both of these expressions so they have the same base. Fortunately, I can rewrite 36 as 6 squared to the x power equals 6 to the 1. These exponents can be multiplied since this is a power to a power, so I get 6 to the 2x equals 6 to the 1. Once the bases are the same, you can abandon them. Take the exponents and make a little mini equation with them. 2x equals 1 tells us that x has to be 1/2. Logarithms have some special properties. The first one is the product property. If you have a logarithm of a product, mn, this separates into a sum of the individual logarithms. Log base b of mn is log base b of m plus log base b of n. The quotient property is similar. You have a quotient, log of a quotient, it separates into a difference. And the power property says if you have a logarithm of a number to a power, that power can be brought around to become the coefficient of the expression. Let's see how these properties work. We're going to expand an expression using the properties. Since I have a quotient here, I'm going to use the quotient property and separate this into subtraction. I'm going to rewrite this as log base 6 of 5x cubed minus log base 6 of y. That's the first property I'm going to use. But notice that now I have a product, so I could separate that product into a sum and make this log base 6 of 5 plus log base 6 of x cubed. And then still minus log base 6 of y. And now I can use the last property, which is this exponent can come around and become a coefficient. And so my final expanded expression would be log base 6 of 5 plus 3 log base 6 of x minus log base 6 of y. Now you can use those same properties to take an expanded expression and condense it. So you have log base whatever, in this case 2, of one logarithmic expression. First of all, let's take any coefficients and bring them back to the exponent position. So we have log base 2 of 40 plus log base 2 of 1/2 squared. So remember, we're condensing now and bringing it all back together. Now 1/2 squared is 1/4, so this is really going to be, and let me at the same time take this sum and turn it into a product, and we're going to end up with log base 2 of 40 times 1/2 squared is 1/4. 40 times 1/4, then minus log base 2 of x. 40 times 1/4 is 10, and the subtraction tells me I can bring this back into a fraction, a quotient. So this will be log base 2, 40 times 1/4 is 10, over x. And now it's condensed. Once it's one logarithm and one reduced argument, then you're done. Now we do have two special logarithms. The common log is log base 10 of x, and you write it without any base at all. So if you see log of some quantity with no base at all, it's understood to be base 10. That's the common log. A natural log is base e, which as we know is the natural base, and when you have log base e, the shortcut way of writing it is ln, which stands for natural log. These are the two buttons you have on your calculator. But what if you're asked to evaluate something like, let's say, log base 3 of 4? You don't have a log base 3 button on your calculator. So fortunately, we have what's called a change of base formula. Log base a of b can be rewritten as log base c, another base of a, over log base c, another base of b. Well, this base that you choose could be a base on your calculator, the common log or the natural log. Let's see that here in this example. I'm going to use the change of base formula and change it to log. This can be log 4 over log 3. And then on your calculator, you can plug these numbers in and get your answer. Let's see what that looks like. If we clear this out, we have our log button, log of 4 divided by log of 3, and that reduces to this decimal, 1.26 approximately. Now you might be wondering, well, could I have used the other button on my calculator, ln? Why, sure you can. What if we had done ln of 4 over ln of 3? Remember, you can change it to that whichever base you want to here. Let's see how that would work. Natural log of 4 divided by natural log of 3. And notice we get the same answer. And so either of those buttons will work, but you'll have to use your change of base formula to access them. Our last topic is solving exponential and logarithmic equations, and there are varying techniques based on the problem that you're given. Let's start with letter A. Notice that the two bases that I have are able to be rewritten so that they have the same base. 9 can be rewritten so that it has a base of 3. 3 squared to the 2x plus 1 is equal to 3 to the 5x plus 1. I don't need to change the base of the right side since it's already a 3. But in doing this, I've now created an additional exponent, and a power to a power means I can multiply those two exponents together. Of course, 2 times 2x plus 1 requires that I distribute the 2. Now, on the left side, I have 3 to the 4x plus 2 is equal to 3 to the 5x minus 1. Now that the bases match, I can take the exponents and make a little mini equation and solve. 4x plus 2 equals 5x minus 1. When I subtract the 4x over, I get x, and when I add the 1 over, I get 3. X equals 3 is my solution. Now notice for this particular problem, I am unable to rewrite the bases so that they have the same base. So now I'm going to have to use a different technique. The variable is stuck up here in the exponent position. I need to somehow release it from this base of 7. Fortunately, bringing in a log of base 7, since it's an inverse operation, it will cancel out that base of 7. I do have to do it on both sides of the equation, however. But fortunately, because these cancel each other out, the 2x just drops out of the exponent position. On the right side, of course, I have log base 7 of 30. I'll be using my change of base formula to get a decimal. Divide both sides by 2. And x is equal to, let's use our calculator to find out what this is going to be. We have log base 7 of 30 can be calculated by saying log of 30 divided by log of 7. And once you get that answer, divide by 2. So this is approximately equal to 0.874. All right, let's try another one. Here in letter C, it's not an exponential function, it's a logarithmic function. But again, the variable is sort of trapped in this logarithmic scenario. To undo it, we need to use its opposite operation, which is exponentiation. If I use a base of 3 on both sides of the equation, exponentiating both sides, the 3 log base 3 cancels out, and the 2x minus 5 drops out of the argument. On the right side, 3 squared is 9. Now it's a two-step equation. 2x is equal to 9 plus 5, which is 14. X is equal to 7. In our final example, I'm going to use one of the properties of logarithms first. Remember, a sum can be consolidated as a product. So I'm going to write this as log base 4 of one argument, x times x plus 6. I'll go ahead and distribute that and get x squared plus 6x, and then that's equal to 2. Now I need the variables to be released from the logarithm, so once again I'm going to exponentiate both sides using the base of the logarithm. This cancels out the logarithm, and x squared plus 6 drops out of the argument. On the right side I have 16. Since it's a quadratic, we should subtract the 16 over, set it equal to 0, and factor. This factors into x plus 8, x minus 2, which gives me two potential answers, negative 8 and positive 2. Now, we need to remember that you can never have the argument of a logarithm being negative. So negative 8 is definitely going to be extraneous, but 2 will be a solution. That's it for today's lecture, boys and girls, and I leave you with the top natural log of e to the 10th power reasons why e is better than pi. God bless you, boys and girls.